So first of all, in this example, it has two parts. I want you to notice the difference between the word verify and the word prove. Proving is what we've been doing so far, where we drew the line in between and we tried to make the left side equal to the right side. And what proving does is proving says that it works for every single angle that's possible. So proving is very powerful. Verifying just says we're going to check one angle and see if it works for that angle. Verifying gives you an idea whether it might be an identity or not, because verifying shows it works for one angle but is nearly not as powerful as proving, because proving shows it works for all angles. The strategies for verifying are almost identical to the strategies for proving, except you'll be using numbers instead of thetas or x's or general angles. So for part A here, for the verify, if you want to verify for 30 degrees, what you do is you still have your left side of your equation and draw a line and your right side of your equation. And now you plug in your 30 degrees wherever you have a theta. And it becomes a pie plate question. What is secant of 30 degrees? Well, cos of 30 degrees is, let's do that one first. What's cos of 30 degrees? Close. Square root of 3 over 2. So if cos of 30 degrees is a square root of 3 over 2, what is secant of 30 degrees? 2 over root 3. And over here, on the right side, we'd have 2 over root 3. Just like a proof, you need to make these look the same. If you get them to look the same, then you're going to be done. Often, you have to do the same strategies that we've done before, is writing things as a single fraction. Sometimes you might get them to be the same before you write them as a single fraction. So algebraically, on the right-hand side, the only thing I could do is write it as a single fraction. So that might be something I do on the right-hand side. What could I do on the left-hand side? I could distribute, yeah. So if I multiplied this by that and that by that, what would I get? Well, 1 times 2 over root 3 will be 2 over root 3. And how do I multiply fractions? Multiply the tops, multiply the bottoms. So if I did that 2 times root 3, I'd get 2 root 3. And if I did the bottom, I'd get 2 root 3. Okay, so we've distributed. What could we do next? You could simplify. 2 root 3 over 2 root 3 is just 1. And we didn't even have to write things as a single fraction because it was equal before we even did that. Can you see that those are the same? So we've proven that they are the same for that one angle. This doesn't make it an identity, but it does say that it works for one angle. In order to make it an identity, we would do the same thing. I'm going to erase this. We've verified it for an angle. When we go to prove, proving says write the left-hand side, so this is secant theta over 1 plus cos theta, and this side is 1 plus secant theta. Now we use our proving strategies. Suggestions how to start. Any ideas? We could distribute the secant theta into the bracket. We could sort of use the same strategy we used with our numbers. if you distribute your secant theta into your bracket, you're going to get secant theta plus secant theta times cos of theta. Okay? We can change this, we could change that secant theta, sorry. This secant theta is 1 over cos. Now, why wouldn't I change the other secant theta to 1 over cos as well? I could. Maybe part of the thing about solving these is sometimes you see a strategy working out for yourself, right? You might see, hey, that this is going to be equal to 1, and then I'm going to be, right, because cos over cos will simplify, and this will be equal to 1, and then I'm done. The left side is equal to the right side. So we were able to prove this by keeping things with secant. Okay? That's one way to prove this question, was with distributing. Sometimes you get into the groove where you're like, I'm getting comfortable with changing things to sine over cos. And so you might just decide to do that right away. So instead of distributing, the very first thing that you do is on both sides, you change things to cos. This is a good strategy because if both sides are only in cos, there's a good chance that if you write things as a single fraction, you're going to get the same answer. So how do I write the right-hand side as a single fraction? Well, I could multiply this 1 by cos over cos, and then I will get cos theta over 1 all over cos theta. If I distribute at this point, or if I think of this, yeah, let's say I distribute at this point, I'm going to get 1 over cos theta plus cos theta over cos theta. I already have a common denominator. If I add the tops and write this one as a single fraction, what do we notice? The two single fractions are identical. And we can again say we're done our proof. So these proofs don't necessarily have only one way to do them. There's often different strategies depending on what you see and how you approach it. There can be shorter proofs and longer proofs. I think the first proof we did was shorter than this one, right? But changing things to sine and cos will also always work. So part B, it said to verify first with 30 degrees and then prove. So let's do the verify. So with the verify, we plug in our 30 degrees. And we go about solving it. From our pie plate, what is tan of 30 degrees? Square root of 3 over 3. So what's cotangent of 30 degrees? Cotangent of 30 degrees will be the reciprocal. So again, we have two sides. We want to verify that they're equal. And what do we notice? Well, we've got fractions with inside fractions on the right. We don't have a single fraction on the left, so if we use our skills to get fractions to be single fractions, this one to get a common denominator, I could multiply by 3 over 3, and I would get 3 minus the square root of 3 over 3 as a single fraction on the left. In order to find out if that's the same on the right, I'm going to have to get a common denominator on the top so that I can multiply by the reciprocal. Can you see my common denominator here could be root 3. And so on the top I'll have 3 minus root 3 all over root 3. And on the bottom, again, I like to make a bigger line for my main fraction, is 3 over root 3. How do we do a fraction divided by a fraction? Multiply by the reciprocal. So I'll have 3 minus root 3 over root 3 multiplied by root 3 over 3. Again, this is one factor because the subtract sign groups that together. And then we have the other factors there. Any factors that are identical? These root 3's are identical. They could cancel. You wouldn't be able to cancel the other root 3's because that gets grouped together. So now, after simplifying that, I have 3 minus root 3 over 3. Does that match up with what we got? Yes, it does. So our left side is equal to our right side, and we have verified now to prove it, we split things up. Again, you could use the strategy of changing things to sine and cos and writing things as a single fraction. I'll show you that. I'll also show you the strategy of changing things to only tan. So one of the strategies that sort of comes up from proving, and you develop these strategies by doing more and more proofs and practicing them. It's not something that you can just see one example and be able to do it overnight. But in this question, if my equation on the left side is with tangent, if I can change everything to tangent on the right side, and then write both things as a single fraction, there's a good chance that they're going to be the same. So I'm going to start with that strategy. I'm going to change cotangent because cotangent is 1 over tan. And then notice that the left-hand side of the equation, well, this technically is a single fraction, right? It's 1 minus tan all over 1. So now, if I could write my right-hand side as a single fraction, I'll probably be able to prove it. Well, how do I do that? I need a fraction on the top divided by a fraction on the bottom. So this 1, in order to get a common denominator, I'd multiply by tan over tan. So I'm going to get on the top 1 minus tan over tan, and on the bottom I still have 1 over tan. And now I have a fraction on the top and a fraction on the bottom, so I can multiply by the reciprocal. Again, this is grouped together. That's a single factor. Do we have any factors that are identical? Yes. These tans will now simplify because those are identical factors. And after that, we're just left with 1 minus tan theta, which is exactly what we had on the left side. Yes? Yeah. So I noticed in this one that I could change both sides to tan. That makes it a good strategy to use. Okay? Let's say you didn't notice that you changed both sides to tan, and you went to the common strategy of, well, let's change things to sine and cos. What would happen? So I'm going to erase what we've done, go back to the beginning, If I change the left side to sine and cos, this would be 1 minus sine theta over cos theta. If I change the right-hand side to sine and cos, I would get cos over sine minus 1 over cos over sine. Again, can you write both sides as a single fraction? Well, on the left-hand side, I would need a common denominator of cos. So I multiply that 1 by cos over cos. And I would get cos theta minus sine theta all over cos theta. On the right-hand side, if I want to get a single fraction, I'd have to get a common denominator on the top. So I'd multiply that 1 by sine theta over sine theta. That will give me cos theta minus sine theta all over sine theta on the top of my fraction, and cos theta over sine theta on the bottom of my fraction. Now that I have a fraction divided by a fraction, I can multiply by the reciprocal. Again, that's grouped together. That's a single factor. But I do have this factor and this factor being identical, so those could be simplified. And so we're all done. So we can solve this one with changing to cos over sine. This work here is going to be sort of a fallback, right? If you're stuck on an identity and you haven't shown me that you can at least change things to sine and cos and write it as a single fraction, then the basic steps of identities you haven't got there yet. So this is sort of the basic steps of identities. Changing both sides to tan, like we did in the first one, is a little bit faster, but that's noticing something first. And then as you practice these over and over again, you sort of think, well, what would be the fastest way to solve for these things? So I'm going to show you a very fast way to do this proof as one last method. One of the things that we use to get a common denominator is multiplying by 1, right? Either cos over cos or tan over tan. We often needed to multiply by 1 to get a common denominator. So I think when I look at this one, I say to myself, what is the quickest way that I could prove this? I'm going to take the right-hand side and I'm going to multiply by 1. And the one that I'm going to multiply by is tan theta over tan theta. So what does that look like? Well, on the bottom, you'd have cotangent times tangent. Those are reciprocals, so that's 1. On the top, if I distribute this, tangent times cotangent is 1 minus tan. Good. Done. And that's probably the quickest way that this one could be proved. But that's using some advanced noticing and some advanced fraction techniques, right? I noticed that if I multiplied tan by cotangent, they'd cancel out and I could distribute, but that makes that a very, very quick proof. So there are strategies out there that make things quicker. You never get docked marks if you take a longer strategy, but you do need to know how to do the basic strategies of writing things as a single fraction. Okay, so questions after this one, 3, 5, 6, and 7. Aye, aye.